Today I will mention 5 different gas laws, but the last one covers all other gas laws and it is the most important one. The name is called as ideal gas law. But before the ideal gas law, I want to mention that these gas laws emerged during the 17th and 19th centuries as scientists studied the relationship between pressure, volume, temperature, and amount of gas. So we have 4 different parameters. And the first 4, firstly, is Boyle's law. The second one is Charles' law. Third one is Avogadro's law. And we have one more, which is the fourth one, and it is the Gay-Lussac law. So firstly, I want to mention all of them. The first one, Boyle's law, is just related with the pressure and volume. So we have 4 different parameters, as I mentioned: pressure, volume, temperature, and the amount of gas. So if there are 2 parameters, then N and T are constant. And this law states that at constant temperature and the pressure of gas is inversely proportional to its volume, or it can be written simply as pressure inversely proportional to 1 over V. So they have inversely proportional to each other. Or if there is a 2 different situation, so it can be written as P1 times V1 equals to P2 times V2. So they are inversely proportional. But what I want to mean that, firstly, in Boyle's law, we have a piston. Okay, it is a movable, and we have a volume and the pressure here. If we put the piston to the another point, and which is the second case, for instance, we decrease the V2. So this is the V1 case. The black one is V1 case, and the red one is the V2 case. Then if we decrease the pressure, if we decrease the volume, then the pressure have to increase. Why? Since they are inversely proportional to each other. And I can also compare the situation, which is the one. So P1 times C1 should be equal to V2 times P2. And this is the Boyle's law. Charles' law is also another important law. And it is developed in 1802, and it is related with the volume and temperature. And at constant pressure, the volume of a gas is directly proportional to its absolute temperature. So what does it mean that? So we have volume and temperature, which means that pressure and amount of gas, or N, are constant. I want to make a piston again. So we have a movable piston, and we assume that there is no leak. It can be going down since the volume can be changed. So if piston go up, then volume increases. If it goes down, which means that volume decreases. And this happens if we heat it. If the temperature of the vessel increases, then we expect to see volume will increase, since they are directly proportional to each other. For instance, if we increase the temperature for our case, and I will make it red, then the new picture should be something like this. Volume should increase. The other law, which is the third one, is Avogadro, who developed this law in 1811, which is called as Avogadro's law. And this law is related with the volume versus amount of gas. Or we can state it as it states that equal volume of gases at the same temperature and pressure contain equal number of particles. We can represent this law by just adding a valve to the bottom of our piston. So I am drawing my best on the tablet. So we have a valve and we can put a gas here. If you put the gas, then number of particles will increase. If the number of particles increases, then volume should increase. But in this case, pressure and temperature are constant. They have to keep them constant to apply this law. And we can write the relationship between two states. For instance, we take a gas, and if we take the gas, this piston decreases since they are proportional to each other. And in this case, for instance, this is V2 and N2 case, and this is the P1 and V1 case. And there's a relationship between them, which is N1 over V1 should be equal to N2 over V2, since they are proportional to each other. Joseph Louis Gay-Lussac in 1808 created Gay-Lussac law. And in this law, we have pressure and temperature directly proportional to its absolute temperature, which means that volume is constant and N is also constant. We cannot change the amount of gas and its volume, which means that if we have a movable piston, it is not movable, so we have a container, we cannot move the piston, which means that if we increase the temperature, the volume will stay same, but the pressure will increase. So they are directly proportional each other, but if I want to compare these two different situations, so we have V1 and T1 temperatures, and we have V2 and T2 temperature in the second case. So if you compare these two, we can write the equation like V1 over T1 should be equal to V2 over T2. Emil Clapeyron created the ideal gas law. So this is the important point. Ideal gas law. And you don't have to memorize the previous equations, but you have to memorize this equation, which is equal to PV equals to nRT. So you are familiar with the P, V, N, and T. P is the pressure, V is the volume, N is the amount of gas, and T is the temperature, but R is the gas constant. So R is the gas constant, and there are many different units of the R. So this ideal law is combination of all the previous laws. This is important. And there are assumptions of ideal gas law, which is PV equals to nRT. And what we assume that gas particles have negligible volume. Gas particles have no interaction among each other. And the third one, gas particles are in continuous random motion and move straight lines until they collide. When they collide, this collision is an elastic collision. And the temperature is directly related to average kinetic energy of the gas molecules. And I want to make an example. This example is not a straightforward example. A chemist has synthesized a compound of chlorine and oxygen and finds that its density is 8.14 gram per liter at 47 Celsius and 3.15 atm. Calculate the molar mass of the compound. So we have to make the relationship between density and the molar mass of a gas. So I have to start with the ideal gas law, which is PV equals to nRT. So we know that N, which is the mole, is equal to mass of the gas over its molar mass. Since molar mass unit is gram per mole and mass unit is, for instance, gram. So in this case, N unit of N becomes small. So we know that this part is good, and we can reorganize the equation, and N over V should be equal to P over RT. And N is equal to M over M. M over M, so M versus capital M. And we have a volume also. I put the M over M to here. And this is equal to P over RT. The other part of the equation is completely same. And we know that M over V, mass over V, is equal to density. So here I can substitute D. So D over molar mass equal to P over RT. And I can take the molarity here, and molarity becomes dRT over P. So we could find the relationship between the density and molar mass of a gas molecule. And I have to substitute it. So the question is right now is very simple. M is equal to dRT over the pressure. So the density of our gas is 8.14 times R. By the way, we should write the units. So if I want to write the unit, it is gram per liter. And R is constant, which is 0.0821 liter atm over Kelvin times mole. And the temperature is equal to 47, 1 second, 47 plus 273, since I have to need a Kelvin and the unit is right now Kelvin. If you want to convert to Kelvin, which is given in Celsius, if you convert to Celsius to Kelvin, then I have to add 373 number. So temperature unit is right now Kelvin, everything is fine, and I have to divide this number to the pressure, which is 3.15 atm. We can make the calculation times 0.0821 times this is equal to 320, I think. Yes, I am right. Over, this is equal to 213 divided by 3.15. So the answer is 67.9 gram per mole. And we should check the units, by the way. Firstly, Kelvin cancels Kelvin, liter cancels to each other, atm cancels to atm, and the unit becomes gram per mole. So unit is correct. And this is all for me. If you have questions, you can use the comment section, and thank you.